Chapter 5, Section 2 is about getting magnetic field from electricity. First, let's remember that we said magnetic field is created by movement of charge. So whenever we have a movement of charge, we have magnetic field. And in grade 11, we have studied current, which is the rate at which charge moves through a conductor or in a conductor or in a wire. Since we have movement of charge whenever we have a current, so whenever we have a current, we also will have a produced magnetic field. If a current passes through a conductor, there will always be a magnetic field. So it creates a magnetic field around that wire or the conductor. This was discovered by Hans Christian Ørsted. He just had his compass with him and he was moving in the room. Suddenly he saw that when he came closer to a wire that was carrying a current, it was deflected. We know that compass only and only deflects if it enters a stronger magnetic field that is stronger than the magnetic field of Earth. And he did some experiments and then published the findings. And then the properties of this magnetic field that's created by the current depends on the shape of the conductor. Both magnitude and the shape. We have three shapes in this section. The first one is a straight wire, and the second one is a circular loop, and the third one is a solenoid. Each one will carry a current, thus they will produce a magnetic field around them. We have multiple circles that have the same center, which is the wire. This is called as concentric circle. So we can say that the shape of the magnetic field at a certain point in a straight wire are concentric circles, and all together they will produce cylindrical shape around the wire. When we bend the wire, the magnetic field will also bend with it. If we make a circle, the magnetic field will be combined at the center, so the magnetic field will be concentrated at the center. In the solenoid, the magnetic field will be similar to this. We have inside the solenoid and we have outside the solenoid. And inside the solenoid, the magnetic field are almost parallel. They are nearly parallel. Whenever we have magnetic fields that are nearly parallel to each other, they will produce a uniform magnitude. So the magnitude inside the solenoid is uniform. And the lines are very close to each other. They are closer to each other than the outside one. So since they are close to each other, it will be producing a very strong magnetic field inside the solenoid. Outside, it is exactly opposite of what we talked about. So the magnetic field lines are not parallel. As a result, they are non-uniform and they are away from each other. So the magnetic field outside the solenoid is very weak. The magnitude of each magnetic field produced by each shape will have a constant at the beginning of their equations, which is called as magnetic permeability. I will talk about that in a moment. And the reason that we have these magnetic fields, they have a current through them. So every equation contains a current too. Let's copy this 3 times. The circular loop can have multiple loops, so you'll have a number of loops here. The solenoid will also have multiple loops, so you'll also have an n in the equation. So mu is called as magnetic permeability. The magnetic permeability of vacuum or free space or empty space is called as mu 0. It has a constant number, which is 4 pi times 10 to the power minus 7. We can say that magnetic permeability is the ability of a medium to be magnetized. So if I put a metal like iron near any of these shapes, it will have a different magnetic permeability. Iron has one of the highest magnetic permeabilities because it has a very good ability to be magnetized as a result, which increases the magnetic field and magnetic flux. I will not talk about the unit of the magnetic permeability. I will write it after writing every equation. Let's focus on the first one, which is the straight wire. Let's choose 3 different points. And we see that the shape at every point is circular. And as we go away from the wire, magnetic field decreases because the circle becomes bigger and bigger. A circle has a circumference, which is 2 pi r. So instead of this r, I will be writing d, which is the distance from the wire, which is the radius of the circle that is produced around the wire, and it is inversely proportional to the circle. So as the circle becomes bigger, magnetic field becomes smaller. So you'll have 2 pi d in the denominator because it is inversely proportional with the magnetic field. In the circular loop, we have a diameter which is equal to 2 times r, and as the diameter increases, the center becomes farther from the sides. So as the diameter increases or as radius increases, the magnetic field decreases. Again, it is inversely proportional. And the last one, which is the solenoid, has a length. As the length increases, the center of the solenoid becomes away and farther from the wires. So again, the magnetic field and the length are inversely proportional. Let's rearrange the solenoid's equation and have mu alone. Mu will be equal to B times L divided by N times I. The unit of B is Tesla, the unit of L is meter, and the unit of current is ampere. And the number of loop doesn't have any unit. So the unit of magnetic permeability is Tesla times meter divided by ampere. The equation shows us the magnitude only. And magnetic field is a vector quantity, so it also has direction. And the direction of the magnetic field for any shape can be found by using a right-hand rule. Since in chapter 5 we have 2 types of right-hand rule, I will be calling this right-hand rule as curling right-hand rule. So I will be using curling right-hand rule if I want to talk about the magnetic field created by a current. Please remember that this is a right-hand rule, so you have to use your right hand. And it only contains 2 quantities, so we only need 2 points. The first one is the thumb, and the second one is the curled 4 fingers. So the 4 fingers must be forming a semicircle. That's how the name is curling right-hand rule. And the thumb is a straight one, so I will be using the thumb for whatever is straight in that shape. In a straight wire, the quantity that is straight is the current because it passes through the conductor, and the one that is curved, the one that is circular, is the magnetic field. Let's copy this. This time the straight quantity is the magnetic field, and the one that is curved, the one that is circular, is the current. So I will be switching places and use the thumb for magnetic field and 4 fingers for the current if I want to use it for a solenoid. What about a circular coil or loop? I can use any of these, both will give the correct answer. But which one would I prefer? I would prefer the one of the solenoid because the equation helps us find the magnetic field at the center of the coil. Let us have some examples for each shape. First, let's start with a straight wire. Notice that if I put the straight wire on the horizontal axis or x-axis, I will have above the wire and below the wire. Let's say that in the first example, the current is toward positive x-axis or it is toward the right side. Above the wire, if you apply the right hand rule so that the thumb is to the right, and since we need to find above the wire right now, our 4 fingers must be above the wire, and the 4 fingers must be above the thumb. So we see that the 4 fingers are coming out of the page. If you want to find the magnetic field below the wire, the 4 fingers must be below the wire, which will be below the thumb too. And if we apply in this way, we see that the magnetic field below the wire is into the page when the current is to the right. In the next example, let's reverse the current. When we reverse the current, always and always remember that magnetic field will also be reversed. If we want to find the magnetic field above the wire, our 4 fingers must be above the thumb too, which is above the wire. When we apply the rule, we see that the magnetic field above the wire is into the page. And if we want to find the magnetic field below the wire, our 4 fingers must be below the thumb, which is below the wire. When we apply it, we see that the magnetic field is out of the page. This time, let's have 2 vertical wires. When we have a vertical wire or on y-axis, we have the right side and we have the left side. Let's have the current as up to the page. If you want to find the magnetic field at the right side, our 4 fingers must be to the right side of our thumb. When we do that, we see the magnetic field is indeed into the page. And if you want to find the magnetic field at the left side of the wire, our 4 fingers must be on the left side of the wire, which is our thumb. When we apply it, we get out of the page. And if we reverse the current, the magnetic field will also be reversed. When we use the right hand rule, we see that the magnetic field at the right side is out of the page because our forefingers is at the right side of the thumb, which is the current. And so here B is out of the page. And if we want to find the magnetic field at the left side, our forefingers must be at the left side again, which is into the page. And now these are in the plane of the page. But what happens when we have the wire perpendicular to the plane of the page? We will have two cases, into the page and out of the page. The current is into the page and the current will be out of the page. When the current is into the page, we see that the magnetic field will be clockwise. We will be using the same rule that we did a moment ago. Our thumb will be into the page, and move your four fingers that has been curled. You see that it will be rotating in the clockwise direction. So the magnetic field is in the clockwise direction when the current is into the page. But if the current is out of the page, again use your right hand rule. The magnetic field will be in the counterclockwise direction. So if the current is out of the page, the magnetic field is in the counterclockwise direction. Remember that at every instant, the magnetic field is tangent to the circle that it creates. It is similar to tangential speed. So magnetic field is tangent to the circle at every point. Now let us have some circles or loop. The current is clockwise this time. So if the current is clockwise, we will see that the magnetic field will be into the page. Use the right hand rule. Have your four fingers rotate in the clockwise direction, and automatically your thumb will be into the page. What happens if you reverse the current? Of course, the magnetic field will also be reversed, which will be in the out of the page direction because the current is in the counterclockwise direction. Let's have some examples for solenoid. We have two windings for a solenoid. When we change the direction of the winding, everything will also change. Remember that in the case of the solenoid, the direction of the thumb shows you the direction of the north pole of the solenoid. It is same with coil. The magnetic field of the coil and solenoid, they resemble the magnetic field of a bar magnet. So we can use them instead of magnets, and we can control them very easily. So let's have the current that is going like this. Use your four fingers and try to follow the direction of the current and grab the solenoid. You will see that the thumb will be to the left side, which means that magnetic field lines are coming out on the left side. If the magnetic fields are coming out of this left side, the left side will be north. Automatically the other side will be south. What happens if the current is reversed? Of course, this time when we apply the right hand rule, so that our four fingers will be moving downward when we grab the solenoid, our thumb will face the right direction. So the right side will be the north pole because the lines are coming out from the solenoid, and the left side will be south automatically. Of course, we have this current if we have a battery, and right side, which is longer, is positive and the smaller one is negative, and the current is always going from positive side to the negative side. And in the other example, it is a reverse. So the left side is positive and the right side is negative, and the current goes from positive to negative. This time let us reverse the winding, and as you see, it is opposite to the first one. On the first one, the winding comes down from the right side, but in this example, the winding is coming down on the left side from our side. Let us have the same source as the previous one, which is the right side as the longer one, which is positive, and the left one is the negative one. The current will be going from positive to negative, so it will be coming down from left side and enters the negative side. And let's complete the direction of the current. So when we grab this so that our four fingers are coming down, you see that the lines are coming out from right side, so our thumb is toward the right side, so the right side is north and the left side becomes south. If we reverse the winding without reversing the battery, the magnetic field poles will also be reversed. This time, let's have the left side as positive and the right side as negative, and the current will go from positive to negative. So it will come down from right side and go up on the left side. When you complete this, we get that the current is going up in our direction, and try to grab the solenoid so that your four fingers are moving upward on our side. The thumb will face the left side so that the left side becomes the north pole and the right side becomes south pole automatically.